A UAV, or unmanned aerial vehicle, is any vehicle that flies and where there's nobody inside.
It can range from a balloon or a quadcopter up to even very small planes.
UAVs have been developed to be able to do tasks in the air without a very high payload, so without needing that pilot. And this enables us to do things, first of all, more efficiently, but especially to perform missions that are maybe too difficult or too dangerous for humans.
They were originally developed for more military applications, but nowadays UAVs are being used almost everywhere. The main reason for this is that they're smaller, they're cheaper, the maintenance costs are lower, and they're more easily deployed.
The project started with the idea of mounting an omnidirectional camera on a drone. On the one hand, it's building this camera, stitching these images, and then on the other hand, it's being able to process all these pixels, but then also processing it in a fast way on board and having also a strong communication link.
The biggest challenge of it all is getting all this done on the small payload of the drone.
It started off 5 years ago with imagine if we had such a drone, what are the advantages and what are the challenges? And then the goal was to get it up and running as far as possible.
The OmniDrone project really started here at ESAT, where a lot of people were working already in the context of drones. We had very good top researchers in the domain of hardware implementation, of vision, in the domain of wireless communication, and we were all passionate about drones. So we started to dream about putting Flanders on the map with this autonomous drone technology. And then we thought, what is still missing? What can we not cover here at ESAT? And then what was missing was, of course, the legal aspects. They're very important when you make drones and autonomous drones. What was also missing was a camera technology, but not just a normal camera. We wanted a 720-degree camera that was small and could be mounted on a drone and could see in all directions with depth information.
Our part of the research is building the 720-degree camera itself and do some autonomous tasks on the video data. So a 720-degree camera is actually a combination of 2 times 360-degree camera. So in a 360-degree camera, you stitch together multiple sub-cameras into one stitched omnidirectional frame. And then we added an extra layer, so it gives extra information, like, for example, depth or the specific 3D positions of persons in the scene.
This was fantastic because it could make our drones just more cognitive, more smart, more aware of its environment, because it can see depth in all dimensions.
The idea is there that we want to extract high-level information in this video. We want to know where the persons are, where the cars are, where the bicycles are, what is the interesting part of the image to look at.
And this, most of the time, it needs to be transmitted to the ground. You need to monitor constantly what's happening at the drone. So you need a video stream on the ground. So you need to transmit it over the air. But a 720-degree video stream is a huge amount of information. If you can imagine, if you try to save this to a file, you immediately get to the gigabytes and so on. So to transmit this over the air is very much of a challenge. Yeah. We approach this problem by introducing new technologies like millimeter wave, massive MIMO, beamforming. Millimeter wave, first of all, because it basically allows for huge bandwidth. You can imagine a one-lane drive. You can pass only a certain amount of cars to that lane, but if you have like 4 lanes or 10 lanes, you can imagine the amount of cars that you can transfer. And one car represents like amount of data. So if you have a very large highway, basically, you can send much more data. A massive MIMO system, we understand. First, the MIMO is basically that there's multiple antennas at one side, so the transmitter, and multiple antennas at the other side, the receiver. Massive MIMO, we mean with this, is that there's a very large amount of antennas. So we're talking about hundreds, maybe even thousands of antennas on one side, which increases the efficiency of your communication system. You have more signals to work with because you have multiple antennas, and combining all these signals, you can have very, very efficient communication. The concept of beamforming is actually that you're combining multiple antennas, and then through mathematics, basically, you can focus your signal to one specific point. The communication relies on the energy that you transmit. So you transmit a certain amount of power, and then at the receiver you need a certain amount of power to read the signal. You can send a certain amount of power in all directions, but yeah, of course, this power is divided. While if you do beamforming, you basically send the power only to one specific direction. So this is actually very efficient use of the power that you need to transmit.
Of course, one way to solve the communication challenge is to do more on the drone and make the drone smarter.
Which means that the drone has to understand its environment. It does scene segmentation, scene understanding. Then it has to know where to go, so it has to do path planning. It has to basically make a lot of decisions of where am I, what's happening around me, and what should I do next.
For me, the autonomy lies in being able to fulfill a task without any human interference. And then the difficulty is in how do you specify the task. A classic problem that we use in our research is collision avoidance, where you have, for instance, a corridor and you need to fly through the corridor without bumping against walls or closets or anything. Other autonomous tasks can be tracking a person. Very popular is with the mountain bikes, that you can spin up your drone and it follows you. There is also a field of autonomous drone racing. The ones that are currently available, they still rely on rules, such as if the person that I'm tracking is further away, I go towards this person. For these simple scenarios, it's enough to work like this. But if you want more intelligent behavior, you need to work with higher resolution images in order to see the details of the task that you're performing. And in order to process these high resolution images, you need strong graphic cards. And these graphic cards, they should work real time, so 10 frames per second at least.
Imagine devices that need to interact with the real world. For example, a robot's arm that needs to pick up an object on a conveyor belt, or even a drone that needs to fly into a certain environment. We want these devices to be able to react to changes in their environment. And we need to be able to do this fast enough. A drone needs to be able to evade an object that comes in suddenly in front of it. And thus, when we talk about real-time software, we mean software that is capable of running fast enough in order to have this reaction time. Obviously, this means that there's no clear-cut definition of what real-time really is. If a robot's arm is able to pick up an object in a few seconds, we might already consider this to be real-time. But a drone that flies at 20 kilometers per hour already covers 5 meters in a second. And so the requirements for real-time software on those devices is much more stringent.
This drone has to perform very complex tasks. And to do that, we have developed computational algorithms that are very powerful, but need a lot of compute power.
There are various different techniques in order to optimize a network. I'll spare the more complex details, but it basically boiled down that we used 3 different techniques. We used depth-wise separable convolutions, we used pruning, and we used quantization. And then we combined these 3 techniques in various ways together.
And you could execute them on super big GPU platforms, but they would require a lot of weight for themselves, for their cooling system. They would need huge batteries that also weigh a lot, and this payload will become too heavy for the drone. Instead, what we do is we develop custom hardware, custom computing chips that can perform the same operations more efficiently, and hence with a very small battery and a very light payload.
Building a fully autonomous UAV is a highly complex problem with lots of different moving parts, and thus there's a need to have experts from various different fields, be it electronics, optics, computer vision.
These challenges really span across the research domains, and you cannot solve them in one research domain. To be very specific, we talked a lot about needing much more complex, intelligent algorithms. You can develop them, but they then result in more compute power. So you solve a solution in one domain, the algorithmic domain, and you push a burden to another domain, the hardware domain, where now a new processor is needed. So there is always this trade-off between bottlenecks in the different fields, and you can only come to a joint optimal solution by collaborating and by really understanding these trade-offs and jointly pushing for this optimal balance between the different fields.
So now at the end of the project, the key question is, when will we have safe and autonomous drones? I believe the technology is almost there, and we have shown this with the contributions we have done in the project. I think the technology is ready, and very soon drones will be part of our everyday life.